Hello, I'm Michael O'Connell, and in today's video we're going to be computing the pressure forces exerted by a fluid within a cylindrical barrel. I have this situation drawn on the board here in which the barrel is actually on its side, and we have the length L, the radius of each end cap R, and then the fluid level within the barrel H. Then we have the horizontal force that's exerted by the fluid actually coming out of the whiteboard against the curved part, 1/2 of the cylindrical surface there. And then we have F sub 2. This is going to be the pressure force exerted against one of the end caps by our fluid that's within the barrel. So in this video, we're going to be trying to find F sub 1 and F sub 2, and those are the pressure forces exerted by the fluid within our cylindrical barrel. Let's begin by computing the pressure force exerted on the curved part of our cylindrical barrel. What do we know about pressure forces? The most important thing about pressure forces is that they're exerted normal to a surface. So you can probably see, based on this drawing here, that we are going to be adding up products of pressure and area to figure out the horizontal component, the overall horizontal force exerted by our fluid on this curved part of the barrel. This is just 1/2 of it. Okay, so with that being said, that does create some difficulty for us because our pressure forces that we're adding up, some of them aren't perfectly horizontal because we have a curved surface. So it'd be really nice if we had a plane in which the forces that we're adding up are all horizontal and we don't have to do any vector resolution in this calculation. And we actually can do that. And I'm going to demonstrate that with my hands. So basically I'm going to bring my hands together like this. And you want to pretend that you're looking down the cylindrical barrel. And basically, if we look at a rectangular plane down this way through the center of the cylindrical barrel, we get a nice rectangle, which is limited, or I should say has a height equivalent to the fluid level. Now, why is that? Because the fluid is what's actually exerting the force on the curved wall here of the cylindrical barrel. So it has some height h and length L. Why is this important? Well, this imaginary plane that I had here that I am trying to help you visualize, obviously you see this is flat, right? It's just a rectangular surface, there's no curve. So where would my pressure forces be along this rectangular surface? Well, they're going to be normal to the surface like that, or like that, like that. And we're just going to add all of these up, right, as we change our height. And we want to do that because, obviously, we're at a higher pressure when we increase the depth within the fluid, okay? So, and we know that from the equation here, where the pressure is equivalent to the product of the density of the fluid, the acceleration due to gravity, and the depth of our fluid, as I said. So, basically, this is way, way better because all of these normal pressure forces, even though they don't look like that because I can't draw in 3 dimensions, are going to be horizontal already. So there's no vector resolution that we need to do. Okay, but we do need to add up all these forces, which is going to require integration, right? So we have to figure out what's changing. Well, specifically, as I said, along this curved surface, we don't have to worry about the length too much. This will actually be a constant when we integrate, right? And why is that? Well, that's because if we go across from one point to another along a horizontal line, the pressure doesn't change, right? H didn't change, so the pressure doesn't change, okay? So that's not something we have to worry about, but as I said before, if we go downward, we have some sort of change in height. This increased, so this would increase, okay? So that's what we have to think about when we're adding up all of these horizontal forces that are exerted by our fluid to get the total horizontal force that's exerted by the fluid on the curved surface. And we would know that that's going to be the exact same against our imaginary rectangular surface within the center, down the center of our fluid, as it is against the curved surface of our cylindrical barrel. Okay? That force is just going to be transmitted because it's the same fluid. And you might ask yourself when you're examining the overall force exerted horizontally on the curved part of your cylinder, well, where did that force come from? Where did it emanate? Well, back at our imaginary rectangular surface in the middle, right? Because we have this barrel, right? And it's made with some material, specifically with some tensile strength, that's going to be able to withstand these pressure forces that the fluid within it is exerting, such that it doesn't explode. So, hopefully that is pretty intuitive, actually, even though it's not something you would maybe think of when you look at this problem. So this actually makes it extremely easy. So let's redraw this imaginary rectangular plane here, length L. And obviously, as I said, we're going to be looking at those changes in height. So we're going to make a small change in height across a strip here, okay? And this is going to be some differential change in the height. And so the product here of dH and the length here, this is going to be our differential area. Okay? And we know that the total horizontal force is going to be a sum of pressure times area products, okay? So basically, we would express that as an integral here. So we would have f sub 1 equals the integral of some pressure multiplied by these differential areas, okay? And we're integrating so that we add up all these strips, okay? So we get the total horizontal force that's exerted out of our whiteboard here at us, that horizontal force exerted by the fluid on the curved part of our cylindrical barrel. Okay, we know what pressure is, that's rho GH. And then we know what the differential area is, that goes in here. So rho and g, density of fluid and the gravitational acceleration, are going to come outside of the integral. H, of course, will stay in. And one thing I forgot, even though I said it before, the length is also constant for our barrel. So that will be out of the integral as well. So we're left with H and dH inside of our integral, which is extremely easy to integrate. The only issue here that is extremely important whenever we do any type of integration is, well, what are your bounds? Well, basically, this force is being exerted by the fluid, and it's going to be dependent on the height of the fluid, right? So this is going to be completely dictated by our fluid level. So up here, our fluid level, as I have here, is 0, and then down here it's H. So H, the fluid level, that's going to be your upper bound, and then 0 is going to be the lower bound. We'll put dashes here so that those are variables of integration. This is easy. So we have rho GL over 2 H squared, and that is the horizontal force component exerted by the fluid against the curved part of the cylindrical barrel. Now let's start trying to find the pressure force exerted on one of the end caps. I'm going to draw a large circle here, and that is going to be our end cap. Okay? This is the center, then we have a radius R. That's a really, really sad circle. And then we have the height of our fluid in our cylindrical barrel here. Okay? So, what do we want to do here? We want to apply the same idea that we applied for calculating the horizontal force exerted by the fluid on the curved part of our cylinder. So, we want to express f sub 2 as the integration of these products of pressure and area, right? So we have this differential area term once again. Okay, so we need to start expressing some of these things, right? So what exactly is going to be changing? Well, we're adding up forces along or against this surface, right? This whole surface, right? Because this is covered with fluid, okay? So we need to find a way to account for those, right? So basically, our interval needs to be some sort of arc almost, right? So we want to start here at the actual height. Once again, we are interested in that change in height, right? Because that's how our pressure changes. Even though it can seem a little weird and a bit uncomfortable to visualize, even when we go down on our cylinder here, or along the surface, I should say, of our barrel, like we're still increasing in depth and the pressure would be increasing as well. So obviously, I've already given a clue there that we're going to have some differential change in height that we want to account for with our integration. But again, we can maybe go from here to where our height begins to where our height ends here at 0, we could say. Okay? This is the fluid level down to the bottom of our barrel. Okay? And so this is what we're integrating. We're adding up all the forces here, then we want to find the total, so we'll just multiply it by 2 in the end. Okay, so how are we going to express this, right? Well, what I think is really, really cool is we can actually just use polar coordinates. It makes things a lot easier, right? Okay, so this is a center point to a point on the surface of our end cap. I don't know why I struggled so much to think of that. So this is R. We can take 0 to be here just like we're going 360 degrees. So this is 0 degrees. And then this is some angle here. We'll call it theta 1. And then we'll go down to here, theta 2. Well, we know what theta 2 would be, right? Negative pi over 2. Okay. And as you might guess, like these are going to end up being our bounds of integration, right? Because they are basically the limits in which we are adding up all of those forces that are exerted, again, out of the whiteboard, the way I've drawn it, on our end cap by the fluid. Okay, so let's start to express some things here. Okay, so once again, one of our terms, just like we had done before, this pressure is rho GH. What is H? Right? That can be like kind of a head scratcher. Well, this needs to be expressed in terms of some theta, right? So some sort of theta. Okay? So how might we do that? Well, we have our height here. We just need to express that in terms of theta. Well, obviously our fluid level is a little higher than just this radius up to the center of our end cap there. But we would have this here, and we know that this line that I've drawn from the center to a point on the surface here of our barrel, that's radius r. And we know that this would be some arbitrary angle theta that we could use. So this is fantastic. If we add this length and this length, we would get our fluid level h. So what is that going to be? Well, h is definitely going to be r plus something. And then this here, so this is opposite over hypotenuse. So this would be r sine theta, right? Because sine theta is opposite over hypotenuse, you multiply the hypotenuse r against sine theta. So there you go. So that's your height. Now, what about the differential area? This is where you're kind of like really, really scratching your head. You're like, how are you going to figure out this one? Well, we're doing the same type of thing that we did before. It's just a little more complicated, right? So we are going to be doing strips once again, right? Because, again, this will give us some sort of constant length, or in this case, we're going to call it width, if you will, that we don't have to worry about that affecting our pressure, right? Because as we move along these horizontal strips, once again, the pressure is constant. We draw these horizontal strips as part of this differential area, right? Because we know that as we change dH, as we change our fluid depth, the pressure changes. So that's why this has to be factored into our expression, and that's why we have the differential area as part of our integral for adding up all of these forces that are exerted by the fluid on our end cap of the barrel. So we would have some width W. So what is W, right? Well, again, this will involve some trig, but hopefully you can see that, again, at any point, like you could ask yourself, well, what would be the width here, right? Well, it would just be this adjacent part for this right triangle, okay? And again, as I'm trying to kind of say, and I don't really want to redraw all of this, but that would be the same just at any point. So if you wanted to know the width at some point, you would have that component, that adjacent component. And then we have our radius r as that hypotenuse. So this, since it's the adjacent, W, the width, is going to be r cosine theta. Okay, now what about the differential change in height? Well, fortunately, we already have an expression for height here. So if we want the differential change in height, we just take the derivative of that. So the derivative of r, that's a constant, the radius, so that's 0. And then this r would stay, but we have the derivative of sine, which is cosine. So actually, our differential change in height also happens to be r cosine theta. Okay, this is kind of a lot, right? So we've actually accomplished the difficult part. I'm just going to erase part of this circle. But honestly, this is the important part, because as I said, we're integrating from here to here, okay, to express the total change in height in which these forces are being exerted by our fluid against the end cap. And then we'll multiply it by 2 to get the other half, okay? And that is going to be helpful for us. So the pressure, we have rho g times this there. So running out of marker here as well. So we would have rho g. Actually, I'm kind of changing my mind here because this is just going to be a lot to write down. So I'm probably going to make a cut at this point in the video. Before I do that, there actually is something else that I do want to address, because I found theta 2 because it's extremely easy, right? It's at the bottom, like you can kind of picture our end cap as its own unit circle, which is actually why I made this part here, the horizontal 0 degrees there. But what would theta 1 be, right? What would that be? Well, once again, we have to remember that this is our height, h. Okay, so we actually know that this part here, so we have the radius and then the height. So this is actually the difference between the fluid level and the radius, okay? That would be the opposite part. And then we have the hypotenuse. Because again, this angle theta, this is that here, okay, projecting. So like, what angle is that? Well, so we have that opposite over the hypotenuse. Okay, so I shouldn't have drawn it that big, but this is going to be the arc sine of that. Okay. And don't worry, I am going to rewrite all of this again. So now I'm going to make the cut and actually erase some of this, and then I'm going to rewrite our integral. Let's express our integral here. So we have our pressure inside the integral, that's rho gh. So we know the height, h, or the fluid depth, I should say. I'm going to just keep calling it the height the whole video, and I'm very sorry about that. But that's going to be r plus r sine theta. Then our differential change in the area is the product of the width and the differential change in height, which are actually both r cosine theta. So that makes this r squared cosine squared theta d theta. Of course, we are going to integrate this as well. What are our bounds for integration? That's going to be theta 1 to theta 2, theta 1 to theta 2, okay? And we can simplify this just a little bit. We have 3 constant terms: the density of the fluid, the acceleration due to gravity, and the radius of our end cap. And then we're actually going to multiply this whole integral by 2 so that we get all the forces, the horizontal forces, included on the other half of our end cap. Because if you remember the profile we had with our end cap, we started at the fluid level all the way down to the bottom of our barrel. So we just are adding up all the forces on one half of the end cap, and we want to get the other half, so we just multiply by 2 because there's that symmetry there. Okay? We can factor out an r cubed, can't we? Because we have r squared cosine squared theta distributed on each of these terms that already have an r. So we can just pull out an r cubed as well. So this will be 2 rho g r cubed. Okay? And then our integral, of course, from theta 1 up to theta 2. And what do we have left? Well, our r's are gone, so this would just be cosine squared theta. You would integrate, you could actually do these by hand. They're not pleasant, but you can do them by hand. And then we would have sine times cosine squared theta d theta. Okay, so basically I was talking about you could integrate this by hand. That would be integration by parts twice. There'd be some other thing that you could do for that as well. Probably maybe some form of trigonometric substitution. But we're not really into doing calculus because this is for transport 1. So I'm not that interested in doing that. And before the video, I was able to figure out what those integrals are so that the video could be a little shorter and we don't have to be doing too much calculus. Although I will say that the rest of this is mostly math because we're just trying to find that final expression. I should have this as equal to F sub 2, which is the horizontal force exerted by our fluid on the end cap of our cylindrical barrel. Okay, so what we're going to want to look at, I'm going to erase all of this actually, is, what that will be and what this will be, which I'm going to write. But what's actually more important, of course, as I like to call our attention to, is, well, theta 2 was negative pi over 2, and theta 1 was the arc sine of h minus r over r. Okay, our bounds of integration are extremely important. Let's start with the easy one. So specifically, this integral here, right? So this is going to be 1/2 times theta plus sine theta cosine theta. This is really, really good for us, okay? And you'll see why in just a second. And then we had cosine squared theta, sine theta. And of course you'd have the d thetas in your bounds of integration. But this is going to be negative 1/3. Oh boy. Cosine theta. Cosine cubed theta, I should say. Now, why is this good? Well, for our first bound of integration here, negative pi over 2, 0, 0, right? So there's nothing to say there. You basically just have your 2 rho gr cubed multiplied by negative pi over 4. Okay, so that's a good first term to keep in mind. Again, I'm going to need more room, so we're going to have to make space. Let's begin working with our other bound of integration. So that's theta 1. Okay, and we remember that it was theta over 2 was our first term. So that will make this part easy for us because this is what we want to remember as I'm doing these, is that theta 1 was the arc sine of h minus r over r. Okay, so this would be subtracted, okay, because it's the other bound of integration that we're working with, so keep that in mind. And then we have the arc sine of h minus r over r. So what about that other term there, right? Because that was added to, obviously we would have the 1/2 again. We had to consider cosine theta 1 times sine theta 1. Well, if theta 1 is the arc sine of h minus r over r, then sine theta 1 is h minus r over r. Okay, so we have that taken care of, right? Now what we want to think about is, well, how do we express cosine theta? Well, to recall some trigonometry from good old Algebra 2, perhaps, and this is actually, I referenced the unit circle with the drawing I made of the end cap. And funny enough, this is exactly where this comes from, is the unit circle. So sine squared theta plus cosine squared theta is equal to 1. So from there, we can subtract both sides by sine squared theta, and then take the square root to get cosine squared theta, okay? So let's think about what that would be for us, right? If this is 1 minus sine squared theta 1, okay? And we know that sine theta 1 is this term here, h minus r over r, right? So then we would have h minus r quantity squared over r squared. We can do a common denominator here, okay? So if that's r squared, we can multiply there, or, sorry, with subtracting, we're subtracting this from 1, okay? So we would have r squared over r that we could use, okay, to actually combine the two denominators. I just wanted to make that clear before I just like started jumping ahead with other steps and stuff. Okay, so that would be our actual expression, again, because of the common denominators. So let's try to get a better expression here for cosine theta. So I'm going to work this a little bit. So what would we have here? So this would be r squared. So that's the expression here that we get for cosine theta. And then we multiply that by 1/2. Okay? So one thing that we could do here is we can take out an r as well. So that obviously is very good. And that will give us a new expression here. Okay, so we just have to be very, very careful, I guess, when we multiply these, right? Because we had, now if we want to take that out of the expression, obviously this part is going to be subtracted once again, so we would have the 2 underneath, and then if we take that out, then we get this expression. And then that was multiplied by h minus r over r. So this is cosine theta 1, this is sine theta 1, then we would have our 1/2. So this part would actually be h minus r radical 2h r minus h squared under that radical all over 2 r squared. Okay, one last term. Okay, hopefully you're not worn out too much already. I'm going to rewrite this expression that we had for cosine theta. Well, why am I doing that? Well, it's pretty obvious because we're going to use it again. Okay, remember we have this minus 1/3 cosine cubed theta term, so this would be theta 1 in our case. Okay, so we are going to cube all of this and then multiply it by negative 1/3. So what is that going to look like? Well, that is going to be adding this expression here, so 2hr minus h squared, all raised to the 3/2 power because it's square root up there. Then, again, don't forget, it was 1/3. And remember, it was minus 1/3. So that's why this is our second bound of integration, so we'd be subtracting a negative. So that's why this is positive. But then we have the 3 in the numerator, and then, of course, that's cubed as well. So that's not really like the most pleasant way you would want to write the expression, but this nasty thing, this is the horizontal force exerted by the fluid within our cylindrical barrel on our end cap. By comparison, earlier in the video, F sub 1, I believe, was 1/2 rho g L h squared. So this was much simpler, where we had that imaginary plane down the middle that we used with that rectangle that allowed all of our forces that we added up to be horizontal, which is amazing. Whereas this, we had a much different profile in which we were changing our heights and thus changing our pressures. So we went with the polar coordinates there with all the thetas, and that was what we were differentiating. Well, not differentiating, but that was the d theta that we had in our integrals. So we had to express a lot of our terms in terms of theta so that we could do the integration to add up all the forces exerted by our fluid on that end cap. So just to reiterate before you go, that this was the horizontal force overall exerted by our fluid on the curved part of the cylindrical barrel, and this, F sub 2, was the horizontal force exerted by the fluid on the end cap of the cylindrical barrel. So I hope this video was edifying. I hope, in spite of the small whiteboard and everything, that you were able to follow along as best you could. Unfortunately, I don't have any sense as to whether or not I am going to be able to actually go to a different place to do these videos, so we might be kind of stuck with this for the semester, but we'll make do with what we have. I thank you so much for watching, and I hope to see you next time.